Okay, so sharpening. So sharpening, we have already mentioned these ideas that an image is sharpened if it has good borders, and borders are in the high frequencies. Okay, so what we are going to do is the boosting of the high frequencies of the images. And the first thing is to relate or to try to understand the behavior of the derivatives with the Fourier transform. Okay, so let us see. Okay, so let us, I will simplify the property. We will not prove it. So the property is, let's say that I have an image with x and y. I can compute the derivative of this image with respect to x, for instance, evaluating x and y. And this image will have Fourier transform. So this image this Fourier transform. It doesn't matter everything. Let's keep it simple. So everything is continuous. So we do the Fourier transform, and we will have now omega. I can also write this one as I of I. Okay, now what is I of omega? So I of omega is the integral over all R. This is a double integral of I x I. I will use R, then E minus A product of these two differential of R. Okay, so now we can compute the derivative of I. But to compute the derivative of I, so I can differentiate the whole thing. If I differentiate the whole thing, I have here a complex exponential. So if I compute the derivative of this complex exponential with respect to x, I will have here omega x plus omega y. This is this product. Okay. So if you differentiate with respect to x, what you have j in front. So if you differentiate with respect to x, what you have is that the j omega x goes out. So the integral, this will be this. So we are not doing the full proof, but we try to understand, we are trying to see where is this coming from. It comes from differentiating these with respect to x. And then this part is the one that comes out. And what happens if we differentiate with respect to y? If we differentiate with respect to y, then this one will be, in the slides you have a 2 pi factor, but this 2 pi factor is because he has defined the Fourier transform with 2 pi on the exponent. Okay, so now also Um, what if, okay, so let's think of these two derivatives. So what is a derivative? We have an image, x and y. We have x here, we have y. And this image tells us that there is a kind of surface here. So I always draw these surfaces, no matter what I can draw. But for any point, I have what is the elevation at that point. What is the height at that point. And then when I'm computing these derivatives, what I'm describing is how much, let's say, this is the red one with respect to y. At this point, how is the derivative with respect to y? So when I travel in this direction, how does this surface change? So if you look from the top, now I will look from the top. So I have y here, I have x here, and I have my function. My function will be, so let's say that my function here is 2. Okay, so my function here, let's say, these are this kind of ISO representations. Have you seen these maps where you have all the points with the same height, you join them with a line, right? So these maps here. So So you have seen this kind of maps, right? So where all these lines, they have the same height. So we can do the same, but now, say all these points, they have the same intensity. Okay, so if I am at a particular point, so I am at this point, and I'm computing the derivative with respect to y, what I'm seeing is how does this intensity change when I'm traveling in that direction. And if I travel in a different direction, if I travel in this direction, then this is the derivative with respect to x. So this is the derivative with respect to x. This one here is the derivative with respect to y. But actually you can travel in any direction. So you can travel in the direction between. You can travel in the direction u. So how does the function change when you travel in the direction u? So let us define that derivative. Okay, so we have normally this is expressed like this. So derivative in the direction u of I. Okay, so this is the limit. So you are in a particular point, and then say h goes to 0 or what? It is the same definition of derivative that we had, but now in one direction. So I will move a little bit in that direction, minus my current position, divided by. So this is the directional derivative. Now, if you are traveling in this direction, this is the u. Okay. This u is there. So you move a little bit in the direction of u, and then you see how much your function has changed. Okay. So yeah, and the partial derivatives with respect to x and with respect to y is nothing special. Only that with respect to x, it is the derivative with respect to x. This is the same of limit I. This is the same as the derivative in the direction 1, 0 of the limit. Okay, we defined the other day the gradient. We remember the gradient. So we said the gradient of a limit is a vector that is the derivative with respect to x I, the derivative with respect to y of I, and then we have the other. Okay, so now, and again, we will not prove it, okay? But this derivative here can be shown that it is this. So this u will have a couple of components, ux and uy. So this is so this is this product. And then I can write that product as u transpose times the gradient. Well, this is the same as the inner product between u and the gradient. So that means that I can compute now derivatives in all directions in Fourier space. Because in Fourier space, I know how to transfer this to. So what is the Fourier transform of the gradient? So what is the Fourier transform of the gradient? If I do the Fourier transform of the gradient is j omega x Fourier transform j omega y Fourier transform. And this is very easy. So all you have to do is you do the Fourier transform, and then point by point you multiply by this, and also the same for y. Now this same idea holds. So what is the Fourier transform of the directional derivative? So the Fourier transform of the directional derivative, I can write it. Fourier transform of these will be this same thing. So it will be the inner product between u and Fourier transform of the gradient. That is a vector. Okay, so please explaining all that here. So this is the property of the Fourier transform. There is this minus sign. I forgot to write minus everywhere. Okay, minus here, minus there. So every time there is a derivative, there's a minus. I forgot the minus. Okay, the minus comes from this minus there. But it doesn't matter. So plus minus, it is a scalar. So scalars are not so important. Okay, good. Then I can sum derivatives and I can compute second derivatives. Okay, so let's look at the second derivative. So we have a function, I have a limit. I can compute the derivative with respect to x. And I can compute the second derivative with respect to x. I can compute the second derivative. Second derivative is first you compute the first derivative, but then you differentiate again. Okay? And I can compute Fourier transforms. So Fourier transform of this is this one. Fourier transform of this is minus j omega x I, and then, so whenever I have a function and I want to differentiate, all I have to do is to multiply by this factor. I have to multiply by that factor. So now I have another function. This is another function. So if I want to differentiate again, all I have to do is to multiply by the same factor. So this would be minus j omega x squared. And we can keep on differentiating if we want. And that gives us a very nice generalization. Okay, so we know this is first derivative, this is second derivative. So this is first derivative, this is second derivative. And I compute the 1.5 derivative. What does it mean? So, and I compute derivatives in between. You can. So you see, this is the first derivative is this factor to the power 1. This is the second derivative is this factor to power 2. So the 1.5 is very easy. It's simply, so the Fourier transform of that one is simply this one, 1.5. And in general, we will call this alpha. So we will call this alpha. So we can compute fractional derivatives. So you can compute the 1.1 derivative, the 1.2 derivative, the 0.5 derivative. So all you have to do is you do the Fourier transform, you multiply by this, then you do the inverse Fourier transform. So we have generalized derivatives in the Fourier domain. Okay, so that is what is explained here. So we are calculating second derivatives now of my image, and it will be the Fourier transform 1, and this is summing the two derivatives at the same time. So we will have the omega x squared, omega y squared. These 2 pi we don't have, because in my definition of Fourier transform we don't have the 2 pi. There are many definitions of Fourier transform, they are not unique. And depending on what is your definition, you have this, I told you before yesterday, the units are radian divided by second. Or so depending on whether you use this 2 pi factor, it is not radian divided by second, but 1 second. That's my definition. And then this minus on the j squared. So let's compute this. Okay, so we take this, we compute it outside. Okay, this will be minus 1 squared, j squared, omega x squared. But this is 1. This is minus 1. And then omega x squared. So the second derivative will have a minus and no j. And this particular image, so we have an image. We have an image. We have the second derivative with respect to x plus second derivative with respect to y. Pay attention to the location of the coefficients. So they are not the same. You cannot put this one here. You have to pay attention to those things. Okay, so this particular combination has a name. It is written like this. It is called the Laplacian. The Laplacian is that sum. Okay, let's think of very smooth images. If something is very smooth, how is the derivative? Large or small? Something changes very smoothly, very slowly, how is the derivative? large or small? Small. And the second derivative, the derivative of the derivative, will also be small. Okay, so for smooth functions, this Laplacian is small. If you have a function that is changing quite quickly, then the Laplacian will be large. And we will use this in some of the papers because it is very difficult to penalize your images, to penalize your results by how smooth or how rough they are. Okay, so the result is, if the image is rough, so changes quite a lot, then the Laplacian will be high. The absolute value of the Laplacian will be high. If it is very smooth, then this one will be small. So we will penalize by this absolute value. So now we have ways of computing the Laplacian either in real space or in Fourier space. Okay, so this is the Laplacian. And so let's say that we have this image, and this is the power spectrum, that image. We multiply by so we will convolve with that kernel. So that kernel, we know what it is. So now we go to discrete images. So we have I of R. So this is the discrete image. And I convolve it with an H of R. And this H of R is just this. I'm drawing the interesting part of it. It is full of zeros everywhere. It is an image, okay? But the interesting part is this one. And we have to remind that we always have to put the origin somewhere. So let's say that this is the origin. Okay, so if that is the origin, then this is equal to what? This is I of R all with now delta R, and this is delta R plus 1 minus delta R plus 1. 1, 0. These are vectors. Okay? I'll write it, I think I'll write it in a different way. It's a bit more clear. Not the same way, but I'll write it in this way. I think it is more clear. So we have delta x y minus delta x plus 1 y. Okay. Now, what is this? So this will have a Fourier transform. This will have a Fourier transform. And we are plotting here the Fourier transform. So this is the Fourier transform. And we saw it yesterday. So we know that these kind of kernels, they are approximations. They are approximations is this sign. This kind of derivative. So it is an approximation to the derivative. So it is not a true derivative, but it looks like it. Okay, so now we multiply, we have it there, and we do the transform, this is what we get. And we are differentiating in this direction, so we see these borders. So we see these borders, these ones. Okay, so this is the positive side, this is the negative side. And then this border here disappears because in this direction there is no change. There is a big jump when you go from at this height. Okay, so you go at this point, there is a big jump. But here in the border of the ball, there is no change, almost no change. And again, now this is the original. And now we add it to the original. Okay, so this convolution. So this convolution. So this will be my image J. This. So this convolution is I convolve with delta. So this is I. Now I convolve with a shifted delta. So that is a shifted image. Is that fine? So this is my original image and then my shifted image. Okay, good. So, and this is a kind of derivative. But now I can construct a new image. Let's call it U. So I will have the image U that will be the original plus my derivative. Then I have I plus I, that is 2I. And then the shift 2I. So I will have whatever I had plus the borders. And as we did before, if you want, you can put in front of the borders, you can put an alpha. So you have here 1 plus alpha. Okay, so that means, okay, add the borders but not too much. So now you have another control that is alpha. So if you put alpha equals 0.5, you are adding only half the borders. Okay, so again, you can be very creative about the way you combine the different images. Okay, good. Then, okay, so you see this expression. This expression is the same. Yeah, this is the one. Okay. Now, what if? Because these kind of convolutions, they are not the only way that I know of computing edges. So now, with all this theory that we had before, all this theory here, I can compute edges in a much better way. So why did we say this is an approximation of the derivative? Let's go. Okay, so what is the Fourier transform of this? So the Fourier transform of this is 1. The Fourier transform of delta is 1. The Fourier transform of a shifted delta is e to the minus j and then omega times the shift. And the shift in this case was this one. This is the Fourier transform of that. So this is my filter. Okay, so this is my filter. And this I can expand if I want. So I can say 1 minus, minus. And now this vector times this one. This is j omega x. And this we can expand further and say, okay, this is cosine of minus omega x plus j sine minus omega x. this is my filter now. And then I can group the imaginary parts and the real parts. So this will be 1 minus cosine omega x plus minus j omega x. Yes. So I'm thinking in the next step, sine omega x. So there is a minus here, but the sign of minus something is also minus the sign of that sign. And now, let's, at low frequencies, how does it behave? So let's say that my frequency is low. The cosine of omega x is approximately what? This is approximately 1. Okay, so this is approximately 1, so this is 0. And then, if the omega x is small, sine of omega x is omega x. So this is j omega x. And now we see, okay, this is the derivative term. So that's why these kind of filters here, the approximations of the derivative. Because the Fourier transform, they also look like kind of similar. So that means that at the beginning, so at low frequencies, this behaves as a line, as omega x, as j omega x. Okay, so, but, okay, this is an approximation. We can do it without any approximation. We can simply multiply by j omega x, and we have seen, for instance, I can also design my filter. What is the important part of this? The important part of this is that I'm multiplying by omega. So I can design my filter in Fourier space. We have the same size. So I can design my filter to be this one. We did this yesterday. If I say my filter will be this, this is the important part of this filter, of this derivative. So it will be a radial filter. So it will be a filter like this. So this is omega x, this is omega y. This will be the modulo of h, and it will be a cone. This is the modulo of omega. And it is now a derivative, but in all directions. Okay, good. Then this is the module. This is the module of your frequency. So now you can take the original image, complete the power spectrum, multiply it by this filter, and do the inverse Fourier transform. And this is what you get. And now you can add it to the original. And you can put thresholds if you want. So you can put thresholds on this image, on the high-pass filter. This HF is a high-pass filter. So you can put a threshold on the high-pass filter image. And then you can detect your borders. And why this one? If I put a square there, now I'm even enhancing more my filters, my high frequencies. So my high frequencies will be now quadratically enhanced. Thresholds, too many things. This is the directional derivative that part of it. So part of it is this directional derivative. So this is the directional. And then after the break, we will discuss about this one. Okay, let's make a break. Break is 29. So let's make a break. Then this. Sí. ¿Lo de qué? ¿Dónde estará?
Si no es la misma. Yo le decía si no lo piensas. Ahí está.
Esta parte. Sí.
Yo tengo una pregunta sobre esto. Porque la convolución del high pass filter y de la imagen vence esa señal.
Porque si yo multiplico esto por esto, voy a tener a frecuencia cero voy a tener cero.
Ah, vale, que la del high pass filter es esa de ahí arriba. Ah,
Claro,
es que no
claro,
la había
claro.
visto. Vale, vale. Vale. Es que no la había visto.
Sí, sí. Eso sí, vaya abajo, vaya abajo. Y el mismo filmaje y se entiende. No, sí, la Del placer, sí. Falta mucho para el placer. Yo sé. patatas de pepino. Yo soy su hija, no hace falta repetirlo todo. Bueno, vamos a seguir. Okay, so let's continue. So, next idea. So, this idea here is about the directional derivative that we have already. Okay, next idea. I think in the slides, if you do it step by step, it is much more clear. So, the next one is that it's a very nice property of images, differentiation, and convolution. Okay, so let's see. The statement will be that you can compute the derivative along any direction of an image. So let's say that I have an image. I convolve it with a kernel, and then I compute the derivative. This is the same as taking my image and convolving with the derivative of the kernel. This is rather surprising. Okay, so first you convolve and then you differentiate. It's the same as if first you differentiate and then you convolve. Why? Because these two operators are linear operators. So if you think in terms of system, so the first one, let's make the first drawing. So the first drawing, we have an image. We go through a filter range, and then we go through a differentiation. And this is our result. But this is linear. This is just a convolution. This one, it is less clear that it is linear, but it is. Let's look at it. Okay, so let's make it here. So now we will prove that this is linear. This, we apply to this, is linear. Okay, so if it is linear, then I can take a couple of images, and we have said that this differentiation is the inner product between u and the gradient of this thing. But gradient is just differentiation. The differentiation. So this is the same. We continue up here. Here, so this is the same as it is, and then differentiating. This is B. So differentiating a sum is summing the derivatives, and scalars, they go out of the derivative. So this is A divided by 1 plus B gradient by 2. But inner products, I can do like this. So I can separate it. I do it into steps. And then I can take the A out. Then this is the derivative of u of I1 plus b derivative of u of I2. So we wanted to show that this operator is linear. So that means that if you take a couple of images, weight them different, and then you differentiate. It is the same as first you differentiate, and then you weight them differently, and you add. So it doesn't matter in which order you do it. So that is linear. So if that is linear, if this system is linear, two linear systems can commute. So now these are aligned because these two systems commute. I can commute them. And these two results must be the same. These two must be. So I can first convolve and then compute the derivative, or first compute the derivative of the kernel and then convolve. And this is very much used. So we have seen these to detect borders. So we have seen you can detect borders. I will use a different word. So to detect borders, detect borders. We have seen that take your image convolve with this kind of kernels. Okay, but these kind of kernels, what happens if I have noise in my image? Then we saw it yesterday with this image that was very noisy. These derivatives will be also very noisy. Why don't I remove a little bit of noise before computing the edge? So I will take the image, convolve with the Gaussian, and then compute the edges. I can do that. And instead of convolving the image, what I can do is compute the derivative of the Gaussian. So I compute the derivative of the Gaussian. And then that derivative, I use it to compute my edges.
But in the first video, when you convolve the image with the Gaussian, you are going to obtain a good image, no?
Yeah, but it has a lot of noise. So I'm trying to remove a bit of the noise.
So you obtain a broad image but with less noise.
Yeah.
And it's better.
Yeah, because if I compute the derivative of something that is very noisy, I will get a lot of noise too. Yeah, remind this one is just a filter like this. So noise is also a very high frequency, so I'm boosting the noise. So first, I dampen the noise at high frequency. This is what this one is doing. Then I compute the derivative. And this is very much used, and you will see it produces very nice pictures. So, for instance, here, derivative. So this is the kind of derivative of the Gaussian. So the Gaussian you have in mind. This is the derivative of the Gaussian. And this is the second derivative of the Gaussian. This is the Laplacian of the Gaussian. So that's very nice. Do you remember our eye response? We will say if a neuron is excited, the nearby neurons are activated, and they are simulated with the Laplacian of the Gaussian. So the function that they use is the Laplacian of the Gaussian. Here you have the three of them. And here you have, this is very nice. These are derivatives in different directions. So this is the Gaussian, this is derivative in this direction, derivative in this direction, second derivative, so second derivative in x, second derivative in y, second derivative in x and y, so what kind of derivatives there. And they are used to highlight different frequency components. Okay, then, yeah, this is this idea here. This we already saw yesterday. It is the same. This guy likes repeating the slides, okay? Just reminding whatever we know. And yeah, all this we know from yesterday. And now, we are in the topic of sharpening. So we take an image, we take the Fourier transform. Now we convolve with this derivative approximator, and these are the borders, and this is the power spectrum of light. And we can add them, and now what we have highlighted are these kind of borders, okay? Because our derivatives are in this direction, so I have highlighted these borders in this direction, and I can do it in what is the difference between left difference and right difference? So look at the kernel. So the kernel, this one is -1, 1, while this one is 1, -1. So it produces the same kind of differences that we will see here. Okay. So left difference, it is 1, -1. When I'm traveling from here and I go from low to high, I will have a positive spike. When I go from high to low, I have a negative spike. With the right difference, that is this one, I have the opposite. So when I'm traveling in this direction, I'm going from low to high, I have a negative spike. Then I will have a positive spike. And you can also look at the location of the spike. So this positive spike is inside my object. This positive spike is outside my object. And again, this negative, this is inside, sorry. So positive spikes are inside, negative spikes, both of them are outside. Yeah, so we have original plus left, right different. Add both of them, add them to the original image. You can do it in the other direction. So yeah, this is all the time the same. We can add all of them and look at this kernel. This kernel is also very much used. It is the sum of the 4 kernels we have seen so far. So we have seen left difference, right difference, bottom difference, so bottom difference, top difference. So we can add all of them, and now we have our sharpening. Just this pair is just to the sharpen, because we like edges. Our eyes like edges. Okay, and this idea we already saw at the beginning of the class. So we can use a low-pass filter to sharpen our images. And the trick is all the time the same. It is to construct a high-pass filter with this low-pass. Actually, this K is a high-pass filter. So it is delta minus a Gaussian. So it is a high-pass filter. So we are adding to the original image, we are adding a high-pass filter version of it. And here it is how it works. So we have the original. Now we blurring. This is 1 minus the blurring. So 1 minus the blurring is RTHs. Now we can add them to the original. Here we have the original and the unsharp. And we can compare to other ways of sharpening. So this is with the Gaussian, this is the quadratic enhancement, the linear enhancement. You may decide which one of them you like the most. I like better this one. And then comes an interesting problem. That is, what happens with noise? Okay, that's good for deterministic images. But what happens with noise? So noise is something that looks like this. Okay, so this is independent, identically distributed noise, and this is now our image model will be this. So my image observed will be an ideal image plus noise at every location. So all this depends on it. Okay, now this noise it has independent, identically distributed. Okay, so those are two qualifications. So independent means you have, this is your noise input. So you have a pixel here, so the noise at the location 1, 0 is totally independent from the noise at the location 2, 0. You know this noise, you don't know anything about this one. Okay? That is independent. That is independent. Okay, and if it is independent, and I compute the correlation, it's the correlation of the noise. So I can compute the correlation of the noise with respect to the lag. This is called the lag. We know this is the expected value of the noise evaluated at that location minus the noise evaluated in different locations. So noise, something that we always assume is that the expected value of the noise is 0. So noise is always 0 mean. Okay, what is this product? This product is you take a pixel, you take any other pixel given by the lab. Now you compute what is the expected value of the product of these two. But if they are independent, that means that that is the product of the two. So this is only valid if they are independent. So it is the product of the two. But one is 0 and the other one is also 0. So this is 0 times 0. So if the lag is different from 0. If the lag is 0, what do I get? Noise squared. So this is equal to this if the lag is different from 0, and it is equal to sigma squared. Sigma squared for the lag equal to 0. So that means this is sigma squared delta. So the autocorrelation of independent noise is the variance. And the Fourier transform, we have defined the power spectrum density. Our Fourier things are always red. So the power spectrum density at a given frequency, that is the Fourier transform of the correlation of noise. So this is the power spectrum density of noise. This is the Fourier transform of this. Is constant, and that is called Y. It's Y because white light has a flat spectrum, and here we have a flat spectrum too. So independence means white. What about the other one? Identically distributed. We have here two names. We have here independent, but we also have identically distributed. So that means if I look at a single pixel, I look at this one. What is the distribution of it. So what is the distribution of the noise at a particular location? This is distributed as what? And it can be Gaussian, can be Poisson, can be uniform, can be whatever, even not any given name. Can be just an empirical distribution. But those two are two different things. One is what is the distribution of the noise. The other one is whether one pixel and the next are independent. So they refer to two different properties of noise. Okay, so Gaussian noise looks like this. So this is, each pixel is independent and each pixel is Gaussian. Okay, it looks like this. This is the histogram of that image. And the power spectrum is almost flat. The autocorrelation is a delta. Problem with sharpening, because let's say, what is our model? Our model is I have an ideal image, then my camera is putting some noise. Then I have some noise. Let's simulate the process. So I have some noise. And I can look at the power spectrum of the power spectra of the tool. So this is the power spectrum of the ideal signal. This is the power spectrum of the noise. And my sum, because they are independent, again, this is an important property of power spectra. Okay, so let's put it here. So the power spectra of I plus n omega is the power spectrum of I plus the power spectrum of n. But there is an important condition for that. I and n are independent. If they are not independent, this doesn't hold. Okay? But if they are independent, then the two power spectra are added. Okay, good. So let's say that our noise is independent from the signal. So we have now a noisy image. So this is what the camera is recording. And then if we think in terms of power spectra, we see that at low frequencies, we have more signal than noise. But at high frequencies, we have more noise than signal. And there is a frequency here at which both of them are equal. And yeah, this was a 1D profile of that, but actually these things happen in 2D. So we have the 2D power spectrum, the 2D power spectrum of the noise. We have the noisy image, that is the addition of the. And now we can indicate which are the coefficients for which we have more signal than noise. So in all these gray coefficients, we have more signal than noise. But I know that because I have simulated my data. If I don't simulate my data, I don't know exactly where, which coefficient has more signal than noise. And this is the opposite. Okay, so these ones, they have more noise than signal. And we can put both. And then, if I apply a sharpening to this kind of sharpening, is this kind of filter. So at low frequency it's fine, and highlighting these borders. But at high frequency, I'm boosting the noise. The noise gets more advantage of this multiplication of high value. And that will amplify the noise. That is why we blur the images before. Otherwise, we would be boosting the noise. So this is the original image. This is the noisy image. It has a very little noise. So, and this is the enhanced original. This is the enhanced noisy image. And then we will make a zoom. So So this is original, this is noisy, and this is the enhanced original, this is the enhanced noise. You see here in the very flat areas, we see a lot of noise. You see? Because we are boosting the noise more than the signal. And here it is the same thing, but now with this image, but the same thing. When you boost, especially when you do very strong boosts, like this one is omega squared. So omega squared suffers more from this amplification of noise than omega. Any question of all these things? I'd like to show you an application of this. Okay, so let's look at a couple of applications. So this is a paper where they will try to correct for blurring. And yeah, it has the last 2-3 days we have been discussing, okay, blurring is not good. Why do we want to blur images? We have found today an explanation why. So if you are going to do a sharpening, you don't want to boost the noise. So first you low pass filter so that you get rid of the noise, and then you sharpen your images. And there is another one. That is, you want to. It is not that you want to blur. It is that cameras blur. So our model before was what I observed. What I observed is an ideal image plus noise. Okay, this is a model of how your observations are. But more typically, what happens is that you have an ideal image that the camera has convolved with something, and then you have noise. So your camera is not perfect. So this is coming from the camera. It is not that you want to convolve it, it is that the camera is convolved. So if you want to correct for this, first you need to understand how convolutions work and how you can simulate that process. Because once, this is called the forward mode. Okay, so let's transform this into Fourier space. So if I transform this into Fourier space, I would say my Fourier transform of the observation is the ideal plus the Fourier transform of the noise. And this one here will be similar, but now with the transfer function of my camera. So transfer function camera plus noise. And now I want to restore this thing. So I want to recover the ideal. What could I do? Okay, I want to recover the ideal. Noise is noise. So noise I cannot estimate. I can try to figure out the properties of the noise. So what is the correlation, what is the spectrum, all this kind of stuff we can try to figure out. But I cannot exactly say what is the noise value at a particular location. It is random. Okay, so let's forget about the noise. Use different words. So I will forget about the noise. So this I remove from my equation. And now I want to solve for the ideal. Okay. The ideal would be whatever you have observed divided by this. And then I have an estimate of, let's say, I have an estimate of what the ideal image should be. And all I have to do is then my image. And I can recover an estimate of what the ideal image. Let's think of a bit of this. Let's say that this filter, this is a low pass filter. Let's say this This is a Gaussian. Okay? Let's say this is a Gaussian with a given signal. If this is a low pass filter, what is this? What is this one? So 1 over a low pass filter is what a low pass filter. It's a high pass filter. This is a high pass filter. It makes sense. If my camera has dampened the high frequencies, what I have to do is to boost it in the same amount. Okay, so that is what these people here in this paper are trying to do. So let's say that I presume that my images are, this is my original image. It has been convolved with a Gaussian. I have added noise, and then I have a scalar there. So this is a saturation model. And we know what saturation is. Okay, so we clip here they are clipping between sigma and 1. Okay, so now once you understand how your models are, how your images, your observed images are formed, now you can try to recover U. And the first thing we will do is, okay, I will presume that this kernel has been a Gaussian. If that has been a Gaussian, which is the sigma of that Gaussian, they will try to estimate from the image. They will try to estimate that Gaussian. And once I have the Gaussian, I will deconvolve. Deconvolve is this operation I have done here. This is called deconvolution. So this is a convolution, multiplication with the Fourier transform. If you divide by it, it is a deconvolution. So I can try to recover my original, but to do the convolutions, I first need to understand what the convolution is and how I can benefit from this convolution. Now you can read the rest of the paper. And let's see some application. So let's go to video. Okay. And then we take this image is nice because it has a lot of borders. Okay. And then what? We can have parameters for the algorithm. We would have to look at what are the parameters. So what is the meaning of those parameters? Here we have the result. So now in the result, this is the input, this is the output. We can compare the difference between them. So you see the output is sharper than the input. So you see better borders. This is a kind of blurring, so the camera has blur, but I'm able to recover it. And more examples of these. So I'll go to my web page. Teaching a course on image processing for electron microscopy. And here we have a few slides on how the micrographs look like. So the micrographs look like this. So all these small spots, they are the proteins you are interested in, and they have a lot of noise. And here, for instance, it is one of these transformations you have already seen. It was the first lecture. So you take the histogram of the image and then you map between the minimum and maximum. But there is also another one that is also very interesting. So this is a virus. You barely see anything of that virus because it is embedded in a lot of noise. So this one here. So each one of these balls is a virus, and you barely see anything because it is embedded in a lot of noise. And then blurring is not bad. And why is it not bad? In this regime, we are in this regime where we have much more noise than signal. So we have so much noise that all this blue area goes to the middle. So we have very little area where you have more signal than noise. So blurring is not bad if you have a lot of noise. Low pass filters. Why low pass filters are good? Because of this plot too. So in general, I cannot know exactly at this frequency I have more signal than noise. This you cannot know. You know if you simulate, but if you record an image, you don't know. But what you know is that in general they behave like this. So at low frequencies, you have more signal than noise. At high frequency, you have more noise than signal. So, and there will be a transition region. So you can estimate what is the size of this circle, and that will be my cutoff parameter. So I will do a low pass filter up to that frequency, or I will use a Gaussian that more or less is similar to this. Any question? No question. Okay, so then we will go for the exam. Exam is there. This one is the